Hi everyone, in this video we are going to discuss about radical axis, its equation and properties. Let's suppose we have a circle like this and another circle like this. Now let's suppose we have a point like this. Let's assume it's a moving point and its coordinates are variable h, k, and let's draw tangents from this point onto the two circles. If the length of these tangents, if the length of PA and PB are equal, then the locus of this point P will be called the radical axis of these two circles. So how would the radical axis look like? Well, it will look like something like this. So this point P will be moving in such a way that the length of the tangents will be equal. And then the locus of this point will be called the radical axis. Let's suppose the equation of the first circle is like this. And let's suppose the equation of the second circle is like this. Now what would be the length of PA? Well, it will be something like this. I have already done separate video on how to calculate the length of tangent. I have shared the link in the description. Feel free to watch that video. But this is the formula for the length of the tangent drawn from an exterior point onto a circle. So the length of PA will be like this, and similarly the length of PB will be something like this. So according to the definition of radical axis, these two lengths have to be equal, then only it will be called the radical axis. If the locus of the point P is the radical axis for these two circles, then PA will be equal to PB. And if you square on both sides, we can say PA squared is equal to PB squared. And now let's replace the values. So PA squared will be the quantity without the square root sign. So we can write PA squared like this, and that will be equal to PB squared, which is kind of like this. And if you carefully notice, we have h squared on both sides, so they will cancel out each other. Also we have k squared on both sides, they will also cancel out each other. So now we are going to be left with something like this on the left hand side, and on the right hand side we will have something like this. And now if we bring all the terms to the left hand side, we can write it like this. And then to find the locus of P, we have to replace h with x and k with y. So the equation will look something like this. And if you carefully look at it, this is nothing but a linear equation. And we can visualize it in a form like this. It looks like something times x plus something times y plus something is equal to 0. So this is nothing but a linear equation, and it represents a straight line. So we can clearly see that the locus of the point P is nothing but a straight line. That means the radical axis is nothing but a straight line. And also if you carefully notice, this equation comes from s sub 1 minus s sub 2 equals 0. That means if we subtract s sub 2 from s sub 1 and we equate that to 0, we'll arrive at this equation. And this is the equation of the radical axis for the two given circles. And if you look at this equation, you will see that it is actually made up of G, F and C from the two equations of the circles. So if we are given the equations of the two circles, we can easily find out the equation of the radical axis. And a few interesting points to be noted here. This equation is of course the equation of the radical axis, and also it is the equation of the common tangent. I have created separate video on this. I have shared the link in the description. Feel free to watch them. So this equation also represents the common tangent when two circles touch each other. For two disjoint circles like how I have in the diagram, it will be the equation of the radical axis. But if the circles are touching each other, then this equation will also represent the common tangent for two circles that touch each other. And also it is the equation of the common chord when two circles intersect each other. So this one equation actually represents three things depending on the situation of the circles, right? If the circles are disjoint, meaning they are far apart, then it will represent the radical axis. Now if the circles are touching each other, it will represent the common tangent. And if the circles intersect each other, this equation will represent the common chord. And that was the property number 1 for radical axis. So far we have derived the equation of the radical axis, and also we have seen the first property of radical axis. Next we are going to take a look at the second property. And the second property says that radical axis is always perpendicular to the line segment joining the centers of the two given circles. So if we assume C sub 1, the uppercase C of course, C sub 1 is the center of the first circle and C sub 2 is the center of the second circle, then the line segment joining C sub 1 with C sub 2, that line segment will always be perpendicular with the radical axis. So this means the product of the slopes of the radical axis and this line segment will be equal to -1 if they are perpendicular to each other. Next we are going to see how to prove it. We just derived the equation of the radical axis, which looks like this. and we can easily convert it into the y equals mx plus c form. And here you see in the x term we have a 2 in the numerator as well as in the denominator, so they will cancel out each other, and from here we can clearly see that the slope of this line is equal to negative g sub 1 minus g sub 2 over f sub 1 minus f sub 2. So that is the slope of the radical axis. Next we are going to find out the slope of the line segment joining the two centers of the circles. The slope of the line segment can be written something like this. If we assume that the coordinates of the center of the first circle are negative g sub 1 comma negative f sub 1, and similarly the coordinates of the second circle center are negative g sub 2 comma negative f sub 2, then from there we can say that the slope of the line segment joining the centers of the two circles can be written like this. And if we simplify this a little bit, it is going to look like this. So we have been able to calculate the slope of the radical axis and the slope of the line segment joining the centers of the two circles. Now let's multiply both of them and see what it turns out to be. Now when we multiply them, you can clearly see that we have similar quantities in the numerator and the denominator. So they are going to cancel out each other, and from here we can easily see that this value is actually going to be negative 1. So that's what we needed to prove. So with this proof, it is clear that the radical axis is always perpendicular to the line segment joining the centers of the given circles. And that was property number 2. Next, we are going to take a look at property number 3. The property number 3 says radical axis bisects the direct common tangent of two disjoint circles. Now for this proof, let me scroll up and I am back to the top again. So here I am going to draw a direct common tangent for these two circles. Let's suppose that red color line that I just drew, that is the direct common tangent for these two circles. And let's suppose that it touches the circles at points E and F. And also let's suppose that it intersects the radical axis at point Q. So by definition of the radical axis, QE will be equal to QF. Those two lengths will be equal. That comes from the definition of the radical axis. And now the direct common tangent is nothing but a straight line, right? So if QE is equal to QF, then obviously Q will be the midpoint of the line segment EF. In this case, let's assume that EF is the direct common tangent, and by definition Q seems to be the midpoint. So the radical axis bisects the direct common tangent. And this proof was fairly simple. I hope everything made sense so far. Next, we are going to talk about property number 4. Property number 4 says that the locus of the center of a circle that intersects two other given circles orthogonally is the radical axis of the two given circles. First, I am going to draw the diagram, and from there we will see what this property means. Let's suppose you have a circle like this, and let's suppose you have another circle like this. These are the two given circles. And now let's suppose that the radical axis of these two circles is something like this. Now let's try to imagine another circle whose center's locus will be the radical axis. And what would be that circle? Well, that circle could be something like this, which actually intersects the two given circles orthogonally. That means the tangents at the points of intersection will be perpendicular to each other, and I have drawn the tangents just to show that this is such a circle, the green colored circle. It is such a circle that intersects the two given circles orthogonally, and in that case the locus of the center of this green colored circle will be the radical axis. Now how to prove it? Let's suppose the equation of the first given circle is like this. And also let's suppose the equation of the second given circle is like this. And let's suppose the equation of this moving circle is like this. I mean the green colored circle. Now what would be the condition of orthogonality for the first given circle and the green colored moving circle? Well, it can be written like this. I have already done a separate video on this topic. I have shared the link in the description. Feel free to watch that video. Now let's call it equation number 1. And similarly, we are going to write down the condition of orthogonality for the second given circle and the green colored moving circle. And that condition will look like this. Let's call it equation number 2. Now, if we subtract equation number 2 from equation number 1, let's see what happens. We are going to get something like this. And then we are going to simplify it a little bit. And then you see on the right hand side, there is a positive c and a negative c, which will cancel out each other. And then if we bring all the terms to the left hand side, we are going to have something like this. And then if we take some common factors out, we could rewrite it like this. And then if we multiply both sides by a negative 1, we can write the equation like this. In the first term, I have converted the positive g into a negative g because we are multiplying by -1 on both sides. So each term on the left hand side will be multiplied by a -1. So the first term can be written like this, and the second term can be written like this, and the third term will become a positive term like this. And on the right hand side, of course, 0 multiplied by -1, that becomes 0 anyways. Now if you carefully look at it, we have the coordinates of the center of the green colored circle in this linear equation. You see this quantity right here, and also you see this other quantity right here. They are nothing but the coordinates of the center of the green colored moving circle. So now we have arrived at a linear equation which is formed with the x coordinate and the y coordinate of the center of the moving circle. Now if we try to find out the locus of the center of that moving circle, then we can simply replace the -g with an x and the -f with a y. Then let's see how that looks. The equation is going to look like something like this. Now if you carefully look at it, this looks like the equation of the radical axis of the two given circles. So as you can see, as soon as we determined the locus of the center of the moving circle, that locus is actually looking like the radical axis of the two given circles. So that means if there is a moving circle which orthogonally intersects two other given circles, then the locus of the center of that moving circle will actually represent the radical axis of the two given circles. And that was the property number 4. I hope things are clear up to this point. Next, we are going to see property number 5. The property number 5 says radical axes of three given circles when taken two at a time are concurrent. That means the three radical axes will have a common point of intersection, and that common point of intersection is called the radical center. Let's try to understand this with the help of a diagram. Let's suppose we have three circles like this, and now I am going to draw the radical axis. First I am going to draw the radical axis between the top two circles. It could look something like this. The equation of the radical axis can be written like this: s sub 1 minus s sub 2 equals 0. We have derived that at the beginning of this video. Next I am going to draw the radical axis between the second and the third circles, and that could look something like this. And finally I am going to draw the radical axis between the third and the first circles, and that could look something like this. Here, the way I have drawn it, it looks like they all intersect at a common point. But somehow we have to prove that in fact they go through a common point. So how to prove it? Let's suppose that common point is R. So if we can somehow prove that the third one goes through the point of intersection of the first two, then our proof will be complete. So what are the equations of this radical axis? Well, I have noted down the three equations here, and then what I am going to do, assuming that the first radical axis and the second radical axis intersect at point R, I am going to try and find out the equation of the family of straight lines that will go through the point R. So using the equations of the first two radical axes, now I am going to try and derive the equation of the family of all straight lines that will be going through that point of intersection. So if we have to determine the equation of the family of straight lines going through the point R, which is the point of intersection of the first radical axis and the second radical axis, then that equation can be written like this. I have done a separate video on this topic. I have shared the link in the description. Feel free to watch that video. Now in this equation, k can be any real number. Here we are going to take k as positive 1 and see how that equation going to look like. When we use 1 for k, then the equation will look like this, and then we are going to simplify it, and finally you see we arrive at an equation like this, which is s sub 1 minus s sub 3 equals 0. Now as you see in the diagram, that is actually the third radical axis. That means using a suitable value of k, we have been able to derive the equation of a straight line that will also go through the point of intersection of the first two radical axes, and that equation seems to be representing the third radical axis. So from here we can say that yes, in fact the third radical axis will also go through the point of intersection of the first two radical axes. This was a tricky proof. Here first we assume that the first two radical axes they intersect at point R, and then we try to find out the equation of another straight line that will be going through the point of intersection of the first two radical axes, and in that attempt, using a suitable value of k, we have been able to find the equation of that third straight line, and that equation actually looks like the equation of the radical axis for the first and the third circles here. So that means that yes, in fact all three radical axes they actually go through a common point of intersection, and that common point of intersection is actually called the radical center. I hope everything made sense. Thank you for watching. See you in the next video.